fully integrating quantum photonic circuits. Since May 2017, he's a member of the Bavarian Academy of Science and Humanities. He has won several awards, including the Dimitris Chorafas Prize, a Fyodor Linin Fellowship, and a Quantum Future Grant. Today, he's going to speak about the dynamics of non-classical light generation based on semiconductor quantum dots. Professor Müller, the floor is yours.
Thank you very much for the kind introduction, Viviana. Let me try to see if screen sharing still works. It did when we tested, so I think this looks good. First of all, I would like to thank the organizers for inviting me to this very exciting workshop here. While it's certainly difficult to do online webinars, I very much enjoy to see that our beloved science still continues under these special circumstances. Just in case that I run short on time at the end of the talk, let me start by acknowledging the people who actually did the work, and the work that I present today is about quantum dots. So that's from my group, the activities led by Lukas Hanschke, together with William Rauhaus, Friedrich Spresny, and Katharina Boos, and Bianca Scarpara. And this work has also been enabled by multiple collaborations. Here locally at TU Munich, I strongly collaborate with the chair of Jonathan Finlay on the MBE growth of samples. The experiments that I present towards the end of the talk have been performed in a close collaboration with Klaus Jöns, who's Zwiller's group, together with some PhD students. And theory and simulation support is provided by Jelena Vučković's group, in particular two PhD students, Kevin Fisher and Rahul Trivedi, and also more theory support from Fabrice Lossi and Elena Deval's group. So my group focuses on investigating optically active solid-state quantum systems with a variety of platforms, and then focuses on using these systems to engineer building blocks and fully integrated circuits that shall have applications in photonic quantum technologies. In my talk today, I'll focus on a more fundamental part, and this is generating single photons from semiconductor quantum dots, and specifically I will talk about the dynamics of the underlying processes. So in the first part, I will talk about the generation of single photons and two-photon pulses from a driven two-level system. Then I will show how to generate single photons with ultra-high single photon purity and discuss their indistinguishability when using a two-photon excitation of the biexciton state. And finally, I'll address the generation of single photons with subnatural line widths. For these fundamental research, we typically work with a broadband sample where the quantum dots are embedded in a lambda cavity on top of an aluminium and gallium arsenide distributive Bragg refractor, which acts as a weak planar cavity now to enhance the collection efficiency. In addition, the quantum dots are embedded in a Schottky diode, which allows us to control the electric field applied to the quantum dots, which can be used to tune the transition frequencies and to stabilize the dielectric environment. Moreover, by carefully choosing the distance between the n-dot back contact and the quantum dot, we can deterministically charge the quantum dot with a single electron. So if we lower the lowest electron level below the Fermi level, then an electron tunnels in, and if we lift it higher, an electron would tunnel out. So we can deterministically choose if we want to work with an uncharged quantum dot or with a deterministically charged quantum dot. And here you can see, for example, in this photoluminescence measurement as a function of the gate voltage, how in non-resonant excitation, the luminescence changes from the neutral exciton to the charged exciton as soon as the lowest electron energy level is lowered below the Fermi reservoir. With such a structure and fully resonant excitation, quantum dots have emerged as a nearly ideal two-level system for testing quantum optics in recent years. So for example, when you resonantly excite this two-level system and tune the transition frequency of your excitation laser, you can see nearly transform-limited line widths. Moreover, when you use a weak continuous wave excitation, you can observe the coherent scattering of the laser. So you observe photons with a subnatural line width that have the coherence and line width of the excitation laser. And if you use short pulsed lasers, you can drive coherent Rabi oscillations, which is very useful for preparing the system deterministically in a specific state. Now, when we want to talk about the dynamics of generating single photons, there are three parameters that are important. The first one is the brightness, and there over the years people have developed different nanophotonic structures, antenna structures that steer the emission in the direction where it can be collected, for example, micropillars or circular Bragg gratings. The second important parameter is the purity of the single photon source. So with a deterministically driven source, the question is how often when you want to get a photon, do you get a single photon, or how often do you have multi-photon errors? And this is related, it can be quantified via the measured degree of second order coherence, G20, which is measured by detecting a single photon at two places in space at the same time. So here, the time delay 0 tells you that two photons from a good single photon source cannot be detected at the same time because the source is pure. The third ingredient that is very important if you think about quantum technologies where you actually want to do something interesting with the photons that you generated is the indistinguishability. So this addresses the possibility of the two photons to show two-photon interference when they arrive at two entrance ports of a beam splitter at the same time. If the two photons are indistinguishable, they will leave the beam splitter in a superposition of both photons going out one exit port and at the same time going out through the other exit port. But you will never see the case that one photon exits each port of the beam splitter. Now, in order to get high indistinguishability, as I mentioned before, resonant excitation is beneficial because it avoids the creation of free charge carriers and the conduction and valence band, which would lead to a fluctuation of the applied electric field and thus to spectral wandering. Moreover, resonant excitation is beneficial because you avoid excitation timing jitter. When you first excite some reservoir from where a relaxation would happen to the state that emits the photon that you're interested in, then the time when this photon is emitted has some uncertainty. And of course, two photons really need to arrive at the exact same time at the beam splitter if they shall interfere perfectly. What helps in addition is per-cell enhancement, because if you now consider that your two-level system would be subject to some spectral diffusion. So although it's a very good quantum dot, let's say it fluctuates a little bit in frequency, so that means that the spectral overlap is reduced. And here per-cell enhancing the emission really helps, because if you increase the homogeneous line width relative to some inhomogeneous broadening, the spectral overlap, as you can see in this simple visualization, increases significantly. And over the past few years, a lot of beautiful works on really high quality single photon sources with high indistinguishability have been published. For example, by Pascal Senelas' group here in 2016, where they demonstrated at the same time a high brightness, low multi-photon probability, and good indistinguishability. And Pascal will talk later on in the session. And I'm very much excited to see how she developed the field from her landmark publication here. What I became specifically interested at that time was to really understand the dynamics of what's going on when we resonantly generate single photons in a pulsed on-demand way. Because much to my surprise, the situation was not that well theoretically analyzed already, because quantum dots have so fast emission rates that it's barely impossible to resolve the dynamics using timing resolution of photonic detectors. So what we typically look at is a pulse-wise integrated form, which is different to other systems which have a lower emission rate, where you can just continuously excite the system and then look at the steady state dynamics. So in order to do that, we established a simulation framework where you define your Hamiltonian. The operators that we're interested in are of the form that is written here. So it's a correlator of operator A at time t, operator B at time t plus tau, and operator C at time t. And these operators can be calculated if you take the dissipation of the system into account, then set up the quantum-optical master equation and use an extended form of the quantum regression theorem to calculate the two time correlations. So this is a conceptually simple approach, but it's kind of resource demanding. My collaborators, Kevin and Raoul, also recently developed a scattering matrix formalism that is conceptually more complicated, but more resource economic. But at the end of the day, you arrive at the same thing. So now we can look with this framework at what happens when we resonantly excite a two-level system. And we see that there are multi-photon error rates, and to visualize them, I use in this talk here not the two-time correlations, because they are a bit more complicated to understand. I use representative quantum-Monte Carlo simulations. So if you now have an excitation pulse here in blue, that drives your system from the ground state to the excited state, the system is prepared and can emit a single photon. However, since the excitation pulse is not negligibly short compared to the lifetime of the two-level system, it can be that while this pulse is there, the system already emits a photon, restarting the Rabi oscillation. So consequently, the minimum value of G2 that you can obtain in simulation depends on the pulse length. So when we calculate these two time correlations and integrate them, we can see that for a resonantly driven two-level system and a pulse length of about 1% of the lifetime, we are in the 10⁻³ range. And the longer our pulse gets, the closer we approach classic light when the pulse is much longer than the lifetime. And this agrees very well with experiments that we performed. Now, in these simulations, we can also vary the pulse area. So now when we look at G2 as a function of the pulse area for a pulse length of tenths of the spontaneous emission rate, we can see that we have a limited G2 If we reduce the pulse area, G2 decreases, which would, in a very simple picture, make you believe that the single photon purity increases. However, this is not exactly the case, because at the same time, when you decrease your pulse area, your brightness decreases, such that you, for a very low pulse area, have something which has a better G2, but has no photon, so it would be a 0 photon source and not a single photon source. Interestingly, when we leave these simulations running to higher pulse areas, we can see that in G2 we observe bunching, which is out of phase with the Rabi oscillations. So this was a bit surprising to us when we first did these simulations, but now you have to remember that what we're doing is we're not driving the system and then asking the question, in which state are you after the excitation pulse is gone? What we're doing is we're resonantly driving the two-level system and at the same time looking at the emission. So we're not looking at the excited state probability. What we measure is the expectation number of the emitted photons. And as you can see here, this is different from the Rabi oscillation, whereby the biggest difference occurs for multiple, well, even values of pi. So now to see what's going on here, we can look at quantum Monte Carlo simulations again, because it's the best visualization. For the quantitatively correct values, it's of course easier and faster to integrate the two-time correlations. When you set a pulse area of pi, the most likely trajectory is that your system is excited when the pulse arrives and then later on emits spontaneously a single photon. If you do statistics, you can see that you predominantly get single photons and occasionally you get two-photon errors. So the emission is dominated by single photons, and the average occupation of the excited state comes from the ensemble average here. Now, when we excite the system with a pulse area of 2 pi, the most likely trajectory is that the system is excited, de-excited again, and no photon is emitted. However, when we look at the most likely trajectory where photons are emitted, we see that these are two-photon emission events. So if photons are emitted, it is the case that a first photon is already emitted during the presence of the pulse. Of course, the emission is most likely when the system is in its excited state, so exactly after a pulse area of pi has been absorbed. This restarts the Rabi oscillation, leading to a high probability to get re-excitation and a second photon emission. So either we get no photon out of the system, or we get predominantly 2-photon pulses. And this can also be seen when we look at the ensemble excited state probability, that you have first the possibility to be excited while the pulse is there, and then see the spontaneous decay afterwards. Of course, we can also do that in experiment. So here you can see the Rabi oscillation of an exciton in a quantum dot. And now we measure G20 as a function of the pulse area, and we observe these bunching for even multiples of pi that we predicted in simulations. What's very interesting here is that these two graphs were not fitted independently. We just took the Rabi oscillation, took into account our measured phonon spectrum and phonon coupling strengths, the pulse length of the laser, the chirp, and the lifetime, so all parameters that we quantify, and theory and simulations are in very good agreement. So this kind of illustrates how far quantum dots have come in the past 20 years. Now we can also investigate this as a function of the pulse length, and the red curve here is when including phonons, but no chirp. The other two curves are when including the chirp that we, at the time when we did the experiment, could measure, but could not compensate for. So without chirp, the bunching that you can obtain is even higher. So now that we understood where this re-excitation that limits G20 comes from, let's try to find systems where we can get rid of this re-excitation and obtain photons with an even higher single photon purity. And here we decided to investigate the biexciton-exciton cascade in a neutral quantum dot. And this is really nice about the electrically contacted quantum dots, that we can deterministically charge them with a single electron and then use the trion as a model 2-level system, or we can work with an uncharged quantum dot and work with this exciton-biexciton cascade. So in this system, the biexciton, so 2 electron hole pairs, have a slightly lower energy than twice the exciton energy, because of the Coulomb interactions of the involved charge carriers. So therefore, it is possible to excite the biexciton in a resonant 2-photon process, where the laser is tuned to half of the energy exactly in between exciton and biexciton, so half of the ground state to biexciton transition. What's beautiful about this scheme is that now our laser is spectrally detuned from the emission, such that it can simply be filtered using frequency filtering. And this spectra here has been filtered with polarization as well, because resonant cross-polarization is what we typically do. Now we can put the laser here. We see the luminescence of the biexciton and of the exciton. And now we can drive these 2-photon Rabi oscillations. So you can really see that we can coherently prepare the system from the ground state to the biexciton. Now, when we look at the system, if after excitation, the system relaxes through this cascaded emission. So that means after a first photon is emitted, the system cannot be re-excited again. Only after the system has been returned to the ground state through this cascaded emission, it is ready for re-excitation. So consequently, the re-excitation should be largely suppressed, and we expect to see significantly lower values of G20. In an example measurement here, you can see this is indeed the case, that no matter how hard we try, we cannot see re-excitation counts here. All that we get is a noise floor from our avalanche photodiodes used for that experiment. Now, if we use the very same quantum dot and measure the resonant excitation of the 2-level system and the 2-photon excitation of the biexciton with cascaded emission, we can see that this cascaded emission has several orders of magnitude lower value of G20, and that this depends on the pulse length. This is very well confirmed in simulations, where it's also seen that because of the cascaded emission, we now have a quadratic dependence of G20 on the pulse length rather than the linear dependence that we observe for a resonantly driven 2-level system. Of course, you can also see here that for these very low values, our data points have quite large error bars, and these naturally occur when you take the statistics of your background from the APDs into account. So here I would like to point to work by our collaborators at Stockholm, who did the similar measurement, but with superconducting nanowire single photon detectors that could be biased in a regime where they don't produce dark cones. And they observe similarly low values, but with a lower error bar. Now we have a system that emits very clean single photons. But how about the indistinguishability of this cascaded emission? To test that, we find a quantum dot that in two-photon interference experiments shows a pretty good indistinguishability. So here it is a single quantum dot that is investigated. It's excited repeatedly, and subsequently emitted photons are interfered. And from the suppression of the center peak in this 5-peak pattern, you can extract the indistinguishability, which for resonance fluorescence looks pretty good. However, when we now perform a two-photon excitation of the biexciton and frequency filter the emission on either the exciton or the biexciton, we find that the indistinguishability is significantly reduced, and it does not matter which one you filter on. For the exciton, you could have argued from the very beginning it's a cascaded emission, so it has some excitation timing jitter, but also the biexciton shows exactly the same indistinguishability. And experimentally, we confirmed this on a number of dots, also grown using different growth techniques. So where does this limitation come from, and how strong is it limited? To do that, now let's first ignore one arm of this two-pass cascade and only look at the cascaded emission of a 3-level system. If we instantaneously prepare the uppermost state and look at the emission of these two states, you can see that the biexciton decays spontaneously. The exciton can only decay after the state has been populated. So any theorist would have told you from the very beginning that these two photons are not individual single photons, but that they are entangled, and that it's impossible to just take one and decompose to factorize the wave function of these two states. So consequently, these are entangled, and to calculate the purity, the trace purity, which is the parameter that theorists typically use to describe the indistinguishability, you have to trace out the other state. And here, our collaborators have numerically calculated that when you instantaneously prepare the excited state, so that makes the calculations easier, you are limited to a value of gamma xx divided by gamma xx plus gamma x, where gamma xx is the emission rate of the biexciton state, and gamma x is the emission rate of the exciton state. So here it's really the interplay of the biexciton emission rate relative to the exciton emission rate that gives you the limit of your indistinguishability. And for quantum dots in the absence of photonic nanostructures, typically gamma xx is twice as large as gamma x. So the value that quantum dot in a bulk environment should show is approximately 66% indistinguishability. Now in our simulations, we can also simulate this case, take into account a finite excitation time. So now it's not possible to calculate it analytically anymore that easy, but with our simulation framework, we can do it. And now calculate the visibility of the two-photon interference as a function of the lifetime ratio. So this kind of tells you that for a quantum dot in bulk, you're limited to this indistinguishability of about 66%. But if you now use quantum engineering to play around with the emission rate, so in particular, strongly enhancing the biexciton emission rate while keeping the exciton emission constant, or even better, strongly enhance the biexciton emission rate while slowing down the emission of the exciton state, allows you for lifetime ratios better or larger than 10:1 to achieve more than 90% indistinguishability. So excellent purity and indistinguishability can be obtained by tailoring the emission rates of the biexciton and of the exciton. So now in the final part of my talk, I would like to talk about the myth of generating single photons with a subnatural line width. Because a few years ago, multiple publications have shown that when you continuously excite the quantum dot using a weak continuous wave laser, that you see photons with a subnatural line width. So this is here the case. We take our quantum dot, the two-level system, excited resonantly, and we see a really narrow emission line that has the line width of the excitation laser. If you now perform a G2 measurement, you see antibunching, which may make you believe that a resonantly driven two-level system under weak driving can emit single photons with subnatural line widths. However, the story is a bit more complicated, because if you plot this peak here in a log plot, you can see that in addition to the coherent scattering of the laser, there is still some incoherent emission from the two-level system with a width of the spontaneous emission rate, so the Fourier transform of the lifetime. You can simulate the coherent scattering and incoherent scattering as a function of the driving rate. And even though it looks like that when you go for very weak pumping, that the coherent scattering is dominating, the incoherent scattering is still not zero. It's spectrally significantly broader, which is why it doesn't appear as prominent when you don't plot the signal in a log plot, but it is still present. So you have the broad peak from the incoherent emission, and you have the small peak from the coherent scattering of the laser. So now we can frequency filter the signal. Without frequency filtering, as I mentioned before, in the G2 of tau curve, we observe strong anti-bunching for zero time delay. So the unfiltered coherent and incoherent scattering produces anti-bunching. But now when we decrease the filter widths to cut away here the part that comes from the incoherent emission and just focus on the coherently scattered light, we can see that with the decreasing filter widths, the anti-bunching vanishes. So as soon as we filter only on the coherently scattered laser, we don't see any anti-bunching anymore. We can analyze now this graph and extract for each filter width the measured value of G2 and now plot that as a function of the driving strength compared to the spontaneous emission rate to obtain these data points here, extracted from the waterfall plot here on the left. They can be very well reproduced by theory, taking into account the actual driving strength. So if you go to a vanishing pumping, so even for the case where you get barely signal at all, you would end up with a red line. When we drive the system a little bit, because we need to get photons to do correlation measurements, we end up with that blue curve that is very well reproduced by the theory of our collaborators, Fabrice Lossi and Elena Del Val. So now this is a very interesting finding, because it tells you that you cannot have, at least with simple resonance fluorescence, you cannot have single photons and subnatural line widths at the same time. Because either you don't frequency filter the signal, then you have single photon emission, or you frequency filter the signal to suppress the incoherent emission and focus exclusively on the coherently scattered part, but then your anti-bunching vanishes, so you only have subnatural line widths and not single photons anymore. It's also interesting with this theory to explore where the anti-bunching in the weak driving regime actually comes from. Because it turns out that the mechanism that is responsible for anti-bunching in a continuously resonantly driven system is depending on how strong you pump the system. So when you strongly pump, which means you saturate the system and you get spontaneous emission all of the time, you have subquarsonian emission. However, when you coherently scatter light, the situation is different. And here what you can do is that you can analyze the interference of the coherently scattered and incoherently scattered part. what theorists do to these ends very often is that they compose the G20 function out of three variables, I0, I1, and I2, where I0 is the sub-Poissonian single-photon emission, I1 is the anomalous component, and I2 is its squeezed state. So here you can see that for strong driving, the component that matters is I0, so the emission of photons with sub-Poissonian light. But at weak driving, anti-bunching results from the interference of the coherently scattered part with a squeezed state of the anomalous part. And what the frequency filtering does is that it affects this balance of interference and results in the anti-bunching vanishing. So of course, now this is kind of bad news because it tells you just taking a two-level system and resonantly scattering a laser does not allow you to create single photons with sub-Poissonian counting statistics or with anti-bunching. But on the other hand, this is also a great resource because now this opens the path for actively manipulating the interference of these states to play around with those and actually engineer photonic states that show subnatural line widths and anti-bunching at the same time. So in summary, I've talked about the generation of single photons and two-photon pulses from a single two-level system. I've talked about the generation of single photons with ultra-low multi-photon probability. And I've addressed the myth of single photons with subnatural line widths. Thank you very much for your attention.
Okay, thank you very much, Kai, for your beautiful talk. Now we will move to a questions and answers section that will be led by Dr. Weinfurter.
Okay, the first question concerns your many simulations. Can you tell us about the framework, what you used?
So the framework here is QTIP. It's all done in QTIP, which is a beautiful free simulation framework. And maybe I can go to the slide again. Where it is. Yes. Here we go. Yes, so QTIP is the quantum toolbox in Python. It's a beautiful resource for simulating quantum physics. And what we did there is that Kevin Fisher, who actually worked on these simulations with me, largely wrote a correlation package for QTIP that you can now download and implement. So there is a new Journal of Physics paper here where we compare or explicitly show the simulations for a resonantly driven two-level system, a non-resonantly driven system, and a lambda system. And linked to this paper, you can also find tutorials for QTIP exactly on the systems that we simulate in the paper. And this QTIP is quite flexible because you can set up your Hamiltonian, so you can also add a cavity, you can add dissipation rates, and then just to calculate the dynamics, use the extended form of the quantum regression theorem on the quantum-optical master equation. The tutorials are very detailed, so if you're interested in these simulations, I can really recommend them.
Thank you. More questions? Actually, I mean, what I was wondering is how much can you take all the dirt effects into account, what you get much more from the quantum dot compared with atoms?
Yeah, that depends on how you do it. So very often it is enough to take them into account with effective rates. So for many simulations, we can just save computational time by reducing the phonon effects, for example, to a phenomenological dephasing rate. However, you can get as detailed as you like. So for example, we've also shown in a PRB in 2015, when we investigated a phonon-assisted excitation for the first time, that you can also plug in your measured phonon spectrum and take it into account using the Bloch-Redfield theorem. So this is one thing. Then also spectral diffusion of your quantum dot, depending on what quantities you're interested in. For some simulations, it's again okay to just take it into account as a phenomenological dephasing rate, but this you can also do more sophisticated, which is something where we're working on right now, that you have a distribution of frequencies. So the framework allows you to do everything, all the dirty effects, but depending on which quantity you're interested in, it gets more and more complicated.
Okay. Thank you very much. Then I guess we can go to the next talk. Thank you.
Thank you.